if we add a opamp with a diode, we can get rid of that constant voltage drop, the model of a diode where it's turned on and has a 0.7 volt drop, or 0.25 or 0.3 for a Schottky or germanium diode, and other values for LEDs and things. It might look kind of confusing, and I really should add in that really, in effect, we really should have some sort of at least a high impedance path to ground. Really a high resistance. Some way to bleed off some charge just to make the circuit really work properly is necessary. You would presume that the output, whatever you attach to the output, would provide that. So even if you attached a scope probe, it would, at least if you're on DC coupling, it would probably achieve that to its 1 mega ohm over some time. So how do you analyze this? We can use the constant drop model. A 0.7 volt drop to understand what's going on. So in this case, with the diode facing this way, if the input is equal to minus infinity, so think about what's going on there. If we have minus infinity here, that will go through the op-amp, and basically that will cause minus infinity here, right? And if we have minus infinity here, the diode is off, right? Hopefully that makes some sense, and you can think about that without too much confusion and mess. So if it's off, then the diode is off, and we have an open circuit. So with an open circuit, this diode connected with some feedback is disconnected. And without that there, we would have VA is equal to minus infinity here, and we would get an output of 0 on the diode. So if I draw the transfer characteristic, we would have minus infinity, we have an output of 0. And that will, well, the question is, where does that go to? We already know that we have this theoretical dotted line, the output equals input. And so where does that come to? Well, we can tell it comes to that point right there, but I'll work through that a little bit more. Because if we're using the constant drop model, we do have that 0.7 volts. So for V in is equal to plus infinity, the diode is 0.7 volts. Okay, so what does this circuit look like then? We have the diode is facing down like that. So the battery goes the same way. 0.7 volts, it goes the same way. Just want to say it's a big output. So we have V out and Vn is plus infinity. And we have 0.7 volts there. And we have a node, which is called VA, between the op amp and the between the inverting, the diode is connected between the inverting pin and VA. Well, we definitely have the virtual short operational in this situation. And with the virtual short working, then the VA wants to equal well, it wants to equal Vn, but in fact, what it really will do is it will, the op amp will cause the right voltage on the inverting pin to be equal to Vn, right? That's what the negative feedback will do. So negative feedback it will make Vn, or sorry, V minus, I should say. It will make that inverting pin equal to V plus, which is equal to Vn, which in this case is plus infinity, right? But it will force this inverting pin to exactly follow the non-inverting pin's input. No matter what voltage and current the op amp needs to supply to VA, it will cause this pin here to be exactly the same as that pin. That's the op amp's job. And so we'll have output is equal to input. And it will go all the way to 0. Just as if it was, we were using the ideal model for this diode, putting this op amp with feedback in there will cause it to follow perfectly correct. And in fact, VA will just be exactly 0.7 volts above this node here. So we'll be 0.7 volts above that. And so I could draw that in. The difference between those two would be 0.7 volts. And something strange obviously happens at the input is equal to 0, but that's what it'll try to do. It will try to be exactly 0.7, VA will be exactly 0.7 volts above the actual input voltage value. If it's 5 volts, then it would be 5.7. And that would be enough to account for the diode drop and cause 5 volts to be on that inverting input.